afternoon. Today we are into the need analysis option. We are studying the unmanned aerial system case earlier, and we are today going to see how we did the need analysis and what are some of the basic considerations that we did. From the previous videos, you have actually seen how the basic user input or user analysis is being collected, where you actually go watch the system, existing system that is in operation, and then look at the users and talk to the users, identify what the user wants, what is the issues with the current system, how the current system can be improved, or what are the lacunas that are available in the existing system, and from there come up with a new option. So, we were discussing the unmanned aerial vehicles, UAVs, earlier, and we have seen a case where we were talking about a short range unmanned UAV that we were developed within as a part of a project. And we said there are so many requirements from the user and how that it actually translated into certain specifications. So, today what we will do is, in a short lecture, we will actually go through how some of those constraints or some of those aspects that were mentioned by the user got translated into what we call as a specification. So, if you remember, we will take two today. So, the first one we would like to talk about is, short takeoff and landing, and second one is should fit behind tailgate of Jeep / Gypsy. So, obviously, these two things we will see, these are two statements that are made by the user, and we will try to see how these statements gets translated to what we call as a type of a specification. So, one thing is that the teams involved in this is, the first team, we will say team 1 is the aerospace engineering team. Second one, team 2, involved this in is the packaging team. Team 3 that was involved in this was the manufacturing, and we also included team 4, the electrical. So, this is what we call as the interdisciplinary team. Okay. So, what we did was, we first wanted to get the size of the UAV. We wanted to know how big the UAV is. So, the right people to give that input, okay, how big in a sense, what is the wingspan of the UAV. The right people to give that input will be the aerospace engineering team. So, their input will be on the wingspan. Okay. The packaging team will be the one who will be decide the carry box. The manufacturing team will be deciding how each parts will be manufactured, or the process they are going to use, what is the minimum pack size that they can manufacture. And the electrical team was wiring and connections, because you will understand when we talk about the details of it. So, if you think about a Jeep or a Gypsy, it's like, if you draw about it, it has a bonnet, it's a cabin, okay, and there is a portion behind it. Okay. This is wheels. This is what we call as the tailgate. So, the idea is that it should, this is where the driver, passenger, everybody sits. The UAV should be able to fit here in a box. So, the package box will go here. Okay. Then the packaging team went and actually took dimensions. So, the step 1 is dimensions of Jeep/Gypsy. So, they took the dimensions and they said, okay, max width is 1.4 meters. So, the wider the maximum width of the component that can fit into the behind is 1.4 meters. And then this input came from the package team. Then the aerospace team suggested between 3 to 3.3 meter wingspan. Okay. So, the 3.3 meter wingspan and then some additional connectors and other things, okay, that was part of this. The 3.3 meter wingspan, if you try to find out how did they come up with that, the idea was that the UAV has to lift something close to 20 to 25 kilograms all up weight, and they calculated a wing area. They took an assumption of about 15 kilogram per meter square as wing loading. And so, in that regard, if you have 2 meter, so per meter square it can actually take up to 15. So, they ended up creating a nice wing which would actually be able to take the hollow weight of 22 kgs, and they said, okay, fine, the wing, this is the wingspan. We are not talking about an aerofoil. This is the, you can think about as the chord, okay, or the distance. So, we multiply this total area should come up in such a way that if you assume 15 kg per meter square, this area, this total area should be able to lift a total weight of about 22 kgs. Once this was finalized, this wingspan was set to 3.3 meters. Once the wingspan was set to 3.3 meters, we knew that there is a packaging restriction of 1.4 meters. So, we took some clearances and other things out, and we found out, okay, if we make this one 3.3 into 3 equal parts, you will get 1.1 meters, which is within this 1.4 meters. So, then we decided, okay, we will make the wing into 3 equal parts of 1.1 meters each. So, then the wing shape came to be something like one part, this is 1.1 meters, and the second part, this is again another 1.1 meters, and the third part another 1.1 meters. Okay. So, that all these, and then obviously if you are making into 3 parts, then you require connections. Because the wings always will have its own control surfaces on it. Your elevators, ailerons, all those kind of things will be available on the wing. So, they are all controlled by servo motors. So, the connections, the wiring has to run through that. So, it was decided that the central piece of the wing, this was the, these two are the end pieces, and this is the central piece. So, the central piece of the wing was mounted onto the fuselage. So, the fuselage was mounted. So, the central wing plus fuselage together 1.1 meters was within this. So, that will actually go as one assembly into the packaging box. Okay. Then these two side pieces of the wing will actually be put onto the sides. That was the way the packaging box was designed. So, based on the packaging team's input, the connectors and other things were taken care of. Then the electrical people said, okay, if you are running all these wires and conduits, then these are the connectors, these are the wires that you need, these are the other additional stuff you need to put it in, which were also taken care of as part of this. So, just to revisit on this one, the central piece of the wing with its own control surfaces was mounted on to, assume that this is the fuselage. This whole total assembly 1.1 meters. Then obviously the second part of this, so this is the width of the, if you look at from the top view of a Jeep or a Gypsy, this is the, if you call this as the bonnet, if this is the bonnet, this is the cabin, and let us say this is the tailgate. The 1.1 meters will fit in within the 1.5 meters. And this length was also measured, and this was matched. So, assume that this is A and this is B. We ensured that B is less than A, so that it actually fits with the packaging actually fits within it. Okay. Once that was over, we were able to calculate the this length was fixed. Then all we need to do is we need to know what is the volume. So, the volume of fuselage was calculated. Then compare with necessary volume. So, what are the necessary volumes? You should have at least a 4-liter fuel tank. Okay. Then avionics, backup battery, gimbal, then you also would require nose wheel steering. So, all these things we calculate what the volume necessary for that by individually calculating this, and when we calculate the volume of what we decided, the size of the fuselage, then we were able to find out that this volume that is available was way much bigger than what we needed. Good. So, we decided, okay, this fuselage is a good design. So, once the general dimensions were made available, then the next thing that had to be done is, there is 2 pieces of wings like this that need to be connected. So, there need to be a connector in between, but also when it flies, this is also a load bearing equipment. So, hence aerospace structural analysis was conducted. So, we studied whether this connector in between has the capability to hold the will take the load, and it was found out that it is better rather than having this, it is necessary to have a connector throughout the length, which is bolted onto the entire central piece of the wing, and then onto the connector these wings will slide in. So, it was a, so this joint was designed as a slide and snap fit. So, then the question obviously raised is, will the snap fit be sufficient enough to hold the wing part? Then it was decided that redundancy using L key nuts. The decision Allen key was used was because it is easy to operate on in any field. You can quickly tighten and loosen the nuts. So, once the wing parts are come in, then there were nuts were provided to tighten them, so that they do not separate during flight. So then the manufacturing team came and told, okay, fine, we can make it provided you give us the specifications and other details. Then it was also decided that these wings, both wing pieces will have its control surfaces, the elevators. Actually not elevators, ailerons. Ailerons. So the size of the ailerons was again provided by the AE department or the AE team. The aerospace team said, okay, this is the size of the ailerons. So then the manufacturing team said the wing will be fabricated in two parts. So the fabrication of the wing was the side parts of the wing was conducted this way. So the side piece, if you take the left side piece, it was fabricated something like this. It was first created this, and then, oh sorry, if you assume this is the wing piece, this much of the wing was weird. This much was built as first part of the wing, and the aileron, this was part 2 and this was part 1. So the manufacturing process made these in two separate parts, and then these were hinges. They were hinged onto the general structure of the wing. And obviously, yes, the airfoil was provided by AE team. The manufacturing team made appropriate molds and then layup process was used to make the composite parts. Obviously, the question here is that why did we choose composite parts? There are a couple of reasons. So there was a discussions on what will be the manufacturing process. Obviously, one option is use aerospace alloys like duralumin and all. Other option is use balsa wood like structure, which is many of the hobby flyers do this, or use high density foam, or use FRP, fiber reinforced plastics. This was ruled out. This is what you call as alternatives. This was ruled out because of the machining cost plus non-availability. Non-availability means this is not readily available in the open market. Balsa wood option was ruled out because that actually do restricts a lot of the manufacturing and as well as moisture and other things. If you fly it in water and other stuff, this will actually create a problem for that. So this was ruled out. Third one was high density foam. Obviously, yes, this is a cheap and a quick manufacturing option, but not the sturdiest of the options. It is good for pattern, but not very good for the final product. So then that is where we finally came down to FRP because it will be a lightweight, durable, strong and weatherproof. Also it is easily complicated shapes can be easily made. So, because all these things, then finally it was decided that the trade off in this process was that okay, we will use composites. So, once this was decided, then the next major thing was what will be the mold or what are the patterns. Then making the patterns, from there the imprint of the part is being taken out. So, that process was started. So, you can see that one iteration of the, so during this process different iterations happened. Initially the wingspan was decided at 3 meters, then it was found that okay, because the earlier design of the wing, the first design of the wing was kind of like a straight edge, something like this. Then somewhere down the road the aerospace team came back and said no, not possible, actually we need to do something like this to reduce the wake turbulence. So, the wing area was reduced. So, when the wing area, this much area is reduced, then you have to increase the length of the wing. So, then the wing length was increased. So, from 1.1 meter initially, it increased to 1.1 meters. So that this missed area was compensated right here, something like this. So, different iterations were happening in this process, and when multiple iterations were created, different version of the product actually, I mean not different version, this is where the initial first prototype, then the prototype was again revised based on the input from the different interdisciplinary teams, and then it kept on revising. Okay. So, this is one aspect of it. Then the second aspect was, once this wingspan and other things were decided, the next option for us is to decide power plant. So, the power plant has two things to do: provide thrust during flight. Second one is provide thrust during takeoff. So, if you want to do long endurance or maximize endurance, this should be minimized. You can't keep on running the entire aircraft at the takeoff throttle. Okay, it's not possible, because you will reduce your endurance. But here also there was a restriction, not here, sorry, the takeoff. The thrust during takeoff was decided like 30-meter runway was the takeoff distance. So, we would be able to provide some 30-meter flat from where the aircraft should be able to take off. So, then the thing was, the power plant became, it can be either electric or gasoline. In electric, what are the options? So, it could be a brushless DC plus propeller. This is some single cylinder engine, approximately 2.5 HP plus propeller. Okay. So, it was decided that we should look into different type of propellers that are readily available. So, the propellers were chosen from readily available options in the market. So, once these propellers were available, then different engines / motors were also procured. The aim was that not to do engine design. The aim of this project was not to develop a UAV engine, it was to actually build a UAV. So, the focus was not built on building an engine, it was more on like choosing from what are the available engines in the market. So, obviously, for gasoline there were like options like Honda, NGH, Roto, GF, then etc. 3W, many options were tried in this case. So, these were the alternatives. In electric, we tried Plettenberg, KDE, etc. Okay. Different type of brushless motors were also tried. These motors were tried with different propellers. So, engine slash motor test rig was developed. To do what? To quantify thrust. So, adding different motor propeller combination or engine propeller combination, we need to quantify how much thrust it would give. So, you are looking at a table something like this, like RPM and thrust. So, at 100 RPM, at 300 RPM, at 1000 RPM, 2000 RPM, 5000 RPM, something like this. You have different RPMs here, and the thrust that were available was also measured. And based on which, also once you measure the thrust, the next thing you measure is the fuel consumption. So, in gasoline you measured how much fuel was consuming. In electric propulsion we are mentioning what was how much of the current it was drawing. Based on which, from here, for different RPM thrust combinations you can actually estimate endurance. So, once the endurance was estimated, we could actually say, okay, fine, for the desired endurance, these are the different combinations of propeller and engine and RPM that we should ideally be planning for. This was a tricky exercise because this required a lot of iterations. Sometimes it is easy to get the thrust, it is not a hard thing to do, but you might be consuming a lot of fuel. So, some of the engines were found out to be extremely fuel consuming, not fuel efficient. So, then alternative options has to be explored. So, from here one option was chosen, which is a balance. This is the most important word, balance. Balance between available thrust and fuel consumption. So, the gasoline engine that was decided for the aircraft, for the UAV, came out of this balance, trying to establish a balance between the fuel consumption and the thrust available. And once it was established, then we were quite sure about the fact that we could actually get the desired endurance from a gasoline engine. Similarly, for the motor, electric motor, the thrust and current consumption was quantified, and based on which appropriate motor was chosen that would actually provide the appropriate thrust and as well as appropriate and as well as minimize the or maximize the life of the battery. I apologize. So, the aim was here to maximize the life of the battery, and here was also to carry the minimum fuel, but gain the maximum endurance. So, once this was done, then we can talk about fuel tank choice or battery choice. So, we know the engine and propeller combination So, this was done from the previous studies. Here also we know the motor and propeller combination. The trick is you can carry as much as fuel as you want. It's nobody is going to create an issue on it. But then the trick is when you carry the fuel, in this case in the here carry more fuel will increase endurance, but will limit other payload. So, on an average we can think about it this way, the payload capability was somewhere close to 8 kgs of total payload including fuel. So, if you carry 3 liters of fuel, that will translate something close to 2.8 kilograms. Okay. If you carry 6 liters of fuel, you can get double the endurance, but it will also become like 5.6 kg. Then you only have very limited quantity left out to carry the carry your payload. Also, it was decided at the same time that in all gasoline engines we will carry a small battery, backup battery, to provide power for avionics if gasoline engine stops during mid flight. So, this is what we call as a fail safe, redundancy / fail safe. When the fail safe was decided that we need to actually carry a battery with us, that reduced the payload capacity of a gasoline system to 6.5 kg, because 1.5 kg was taken away by the battery. The 1.5 kg was needed because that much of battery is necessary to manipulate the control surfaces, and if the aircraft is 70 kilometers far away, you should be able to bring it back. That is a glide ratio was calculated into this regard. Okay. The glide ratio of the UAV was 1 in 20. Okay. So, for every 1 meter it falls vertically, it will travel 20 meters horizontally. So, it is a very good glide ratio available to this aircraft. This was the glide ratio. Okay. So, if you think about it this way, if you are flying at an altitude of 1000 meters, then if the altitude is 1000 meters, if you drop 1000 meters, it can actually travel 20,000 meters travel. It is about 20 kilometers. Okay. So, we can easily think about it in such a way that the UAV was flying at 5,000 feet, 5,000 meters, then you know how much it can actually travel. So, then from there we calculated, okay, to that much distance, how much of electricity is needed or how much of energy is needed to maintain the autopilot or the avionics continue to tick on and provide telemetry and other things. So, based on which the specific battery was chosen, and that battery's weight came to be something 1.5 kgs. Let us assume it was less than that, but at this point for ease of calculation we are taking it as 1.5 kg. So, we had a payload of 6.5 kg available. So, immediately we know that this 6 liters of fuel is ruled out, because you rarely have now 900 grams left for your payload. So, to do this case we have to do weight optimization further and increase the payload capability. But for that initial design we were like, okay, this was not feasible. So, for the initial design what happened was the fuel was designed to be 4 kgs of fuel, 4 liters of fuel, 4 liters of fuel for the initial flight. Then the rest of it was reserved for the payload. Now, here once this calculation was going on, a team that was interfacing us was the electrical team, then control team and the payload team. So, the payload team said camera plus power module weight equal to x kilograms. They said some weight. The control team said avionics weight equal to y kilograms, and electrical team said wiring plus other stuff weight equal to z kilogram. So, the thing that we had to do was the x plus y plus z should be within the available space available. So, this was given us as a number to us. So, we basically got an idea that this will come somewhere close to about 2.5 to 3 kg. Once we have a ballpark figure of this, we could always reserve a 3 kg separate and then work on other things. Pretty soon it was evident to us that the initial design we are going to be really pushed for weight, or we have to find some way to do weight reduction. So, then the further it was established the need for reduction in weight because why was this necessary? Because maximum takeoff weight or MTOW was fixed somewhere at 22 kilograms. We could not do better than this because of the takeoff restrictions. Okay. This was the takeoff restrictions. So, once this was there, we said okay fine, no matter what happens we have to reserve somewhere close to 3 kg for payload. Okay. So, once these things were calculated out, then we said okay fine, airframe weight needs to be reduced by 2 kg around. So, then back to AE team, aero team plus manufacturing team. So, they said well, current foam cannot be changed, or they said instead of cannot, should not be changed because it is quite optimized. Then obviously, when the aero team gave that input, then we looked at the manufacturing team. Then they said okay, let us include other materials that will allow for weight reduction but will not compromise on strength. So, the material was, the manufacturing process got revised to include FRP, fiber reinforced plastic, plus carbon fiber, because when you add carbon fiber with FRP, it will actually give you much more strength, plus aerospace grade. We are using the term because everybody knows is commonly Kevlar or aramide, okay, fabric. So, or this is the right name is aramide. Okay. So, this process, instead of just FRP, would allow us to reduce the number of layers that are necessary to provide the strength. In that process, reduce the weight, and then through this manufacturing process, we were able to shave off somewhere close to 2 kgs, approximately 2 kgs from the structure weight. So, this 2 kg shave off from the structure weight directly helped us to carry, allowed us to carry a little bit more fuel. Then we went back. So, this is the time where we came back to the aero and the manufacturing team, and we went back to the, from here we went back to the payload team for weight optimization. So, then they worked on the gimbal and the camera and other things, and they were able to shave off another 300 grams. Then we went to the avionics and the control team. So, then the next thing was the avionics team. They shaved off another 300 grams. So, we did multiple iterations, multiple loops, because our airframe weight was constrained, and in this process we were able to get another 700 grams shaved off from different places, which actually gave us quite a lot of luxury. Once this exercise was completed to a reasonable extent, then we decided, okay, fine, it's time for us to build the prototype now. So, in this process, by splitting it into different parts, we are also able to identify what are the components. So, if you think about it, the things in this process, main achievements were like identified power plant. It was decided as a COTS, commercially off the shelf, identified propellers, that was also COTS. Third is structure, make it ourselves. Okay. For battery, COTS, then it was the control system, it is avionics, okay. It was assembled using COTS. These are sensors, chips, etc. Okay. Then we also had the gimbal, the payload mount. You can think about it this way. Okay. Make plus use servos. These were COTS, commercially off the shelf servos. Then 7 would be payload, which were cameras, COTS, commercially off the shelf. We are not in the process of making cameras. Then was the communications. Okay. It again COTS, antenna. We had amplifier, power source, mount, etc. These were all procured directly commercially off the shelf. Then obviously the software in home. So, this was built by ourselves, and then it was ground control. This was a ruggedized laptop, again COTS. So, if you think about it, it was actually an assembly of lot of the COTS commercially off the shelf systems, available off the shelf systems, but intelligently put together. So, you can think about this entire structure, which is the most important component. So, this you can think about as about 60% of the whole thing is completely done, And as well as you can think about it, this control system assembly, you can think about as, okay, I will probably put the structure at a little bit more of a lower rate. Let's say, let's put it as 40% instead. This would be like 20%, and then software would be another 15%, right? And gimbal, this would be another 10%. Okay. So we think about it, 40 plus 20, 60 plus 10, 70 plus 80, about 85% of it, we can assume that it was in different phases. It was built in ourselves using a different, like if you ask the question, obviously, as in this case, who made carbon fiber? Who made carbon fiber? The answer is procured, because we don't have the technology to make it at this point. But using the carbon fiber, we were able to make our structure. So in many times, systems engineering is not about building each and every component. It's about building what is necessary to be built and using the materials that are available quickly, and build in such a way that the critical components are built and done with you. So the most critical components, the structure, the control system, the software, and as well as the gimbal, the control of the payload, was pretty much built in-house. And obviously, other part we would be thinking about next would be to take care of the and then the communication aspect also. Even though the antennas and other things were bought from outside, the communication, the encryption and other things were done as part of the project itself. This would be one area where obviously, yes, if you want to gain superiority, you need to put more research and other things into it. So that would be something. This is a new technology avenue. This is something where we need to demonstrate the capability of the technology. So that will be a spin-off from this systems engineering or system development process. Okay, we need to now gain expertise on the small single cylinder engine that can be used in UAVs. Fine, that's a new technological ground, but that should not limit the development of the UAV. That is what is the most important part of that. Now, once all these aspects were taken, were decided, then the next thing to be done is the process. So, build initial prototype. This was built using HDF, high density foam. Okay. Only structure plus propulsion plus control system. This was done purely because of that these three things. Okay, once it is finalized, when you have sufficient confidence in this, then you can add the payload and as well as the communications as part of it. So multiple iterations conducted. Iterations were made again. Okay. Optimal design was chosen. Final molds for fabrication approved. This much was done from where the metallic molds for composite parts manufacturing was built. So we built the molds from after this process was over. Then from there, the payload, before the payload, the communication module was incorporated with the composite model. Then endurance, range, reliability, these were tested. The reason payload was taken out of this picture was due to the payload not used because of the expensive nature of cameras. The cameras were all expensive, and we decided that it was not a good thing for us to really really break the camera while doing these tests, because the project funds were also limited. So we didn't have money to break few infrared cameras and few electro-optical cameras. So the payload was not part of this. So by the time this whole process was over, 4 parts: airframe plus propulsion plus control plus comms or communications. This was completely tested out, and we had quite a good confidence in the system that we know, okay, fine, it is time for us to third step, integrate payload. So payload was integrated onto a well tested system. So if any failure happens, then the failure is only due to the payload. So what happens is that the testing, this is actually what we can say is that test as you build. Test. So it is not that you build everything and then test. You keep on testing at each phase, each iteration. Okay. When you build the high density form model, test. From there you approve everything, after that test. From there you add comms module, then test. So every integration, every new addition, every new revision, every new addition of the new system into the new component in the system, testing is a lifeline of developing a new system, because without testing it is impossible to actually establish the viability of a complicated system like unmanned aerial UAV system. So with all these kind of things, I think you probably would have an idea of a roadmap of how we went about in developing an unmanned aerial UAV system, a small UAV system. And in the next class, what we will do is we will actually look into what are some of the forms and other things, or what some of the standards and other establishment, other established systems engineering techniques that we used in this process. So I will try to expose you guys to certain techniques as part of this course, and see how this actually works in the development of a new system. Thank you.